Good morning and good afternoon, ladies and gentlemen. We've got a global audience today, so it's morning for us in the UK and afternoon for some of our colleagues over in Asia. So welcome to our webinar today, and we're going to look at flood data for Asia. So thank you very much for sparing your time. Now, at the Oasis Hub, we work with a range of different partners and that provide data, tools and services. And for this particular project, we've been working with Fathom Global. After this brief introduction, we'll start by looking at flooding on a global scale and then quickly bring the focus to the impacts it has within Asia. Next, we'll drill into the data and looking at how it was developed and back that up with some real-world case studies. And finally, we'll close with questions and answers. And I'll just spend a moment explaining how you can do that using your webinar control panel. It looks similar to this. You might get some variations and differences if you're running on a mobile device. So you can control things like your audio settings, your speaker and microphone volumes. If you want to ask a question, click the Q&A button, which opens the Q&A panel. Type your question in and then press send, and please feel free to do that at any time, and we'll do everything that we can to answer questions as we go through the webinar. Any questions we don't get to during the webinar, we'll deal with in the Q&A session a little bit later on. Now, what I'd like to do is introduce you to our hosts. I'm very pleased to be joined by Dr. Chris Sampson. Chris is the Chief Technical Officer at Fathom Global and one of the founders. He's a graduate of the University of Bristol, where he studied a Masters of Science in Physical Geography, graduating with a first-class honours. He then progressed to a PhD under Professor Paul Bates, which focused on the development of catastrophe models for flood risk for the reinsurance market. So Chris is very much a leading expert in the development of large-scale hydraulic models. And I'm Jim Craig from Oasis Hub, and I look after what is essentially product management and product marketing. What I'd like to do now is set some context at a global scale, project forward in time a little bit, and then focus on Asia as a region. Almost a third of global economic losses are due to natural hazards. Almost a third of global economic losses due to natural hazards are due to flooding. So that's a significant proportion of losses. The top 10 costliest floods, looking at the 34 years between 1980 and 2014, we can see that over 13,500 lives have been lost, with many millions more affected. Financial losses are approaching almost $200 billion US. So if we project forward just 12 short years, the estimate is 54 million people will be impacted by flooding, with economic losses more than doubling to $521 billion US. Changing land use can make significant impacts on flooding. Rapid, unplanned urbanization can leave populations exposed to increased flood risks. By 2030, an extra 200,000 square kilometers will be in high frequency flood zones. So what does that mean for Asia? If we bring it more down to a regional focus now, these are just some of the events that have impacted Asia in recent times. In 2018 is a La Nina year, which is expected to increase flooding in Bangkok. In April 2017, up to 1 meter of flooding was experienced in low-lying areas of Ho Chi Minh City, causing havoc at the Tan Son Nhat International Airport and halting trains in the Thu Duc district. In May this year, Manila was hit by torrential rain that brought the city to a standstill, with floodwaters chest deep in places. Tropical storm Trami brought in an extra 30 millimeters of rain per hour. And then a little further back in time, in 2014, the Pakistan military helped move an estimated 6,500 people in and around Lahore due to flooding. Lahore is where half of Pakistan's 180 million population live. So, big problem. Chris, what can we do about it?
Okay, thanks, Jim. Can I just check that the sound is working? Okay, fine. So this is an example of what you might see from a typical engineering grade flood model. So where you've got very high quality terrain data, you've got lots of information about the river and the defenses and the storm drain network, and you've had people out in the field, you can produce models that look like this. This is actually a simulation of the 2005 floods from Carlisle in the UK, built at a 2-meter resolution. And the error in a model like this is down to about 25 centimeters. So they're incredibly precise, and these are the sorts of tools that engineers use to make decisions about flood risk on a day-to-day basis. But as you imagine, or may imagine, I'm going to try and move a slide on, Jim, but it doesn't seem to be behaving for me. Okay. Yeah. As you zoom out to much larger scales, as we move towards territories that don't have such readily available high quality data, the problems of building flood models become very severe. And you know, this is because flood models are very complex things. They have to operate at high resolution, and that makes them very data hungry, both in terms of quantity and quality. And so if you're thinking about building a flood model in the developing world or anywhere that you don't have high quality information, you have to think very differently to how you might build an engineering grade model. And nice. Jim, can you, yeah, okay, fine. Let's go. I'm sorry about these slides, folks. They don't seem to be advancing in the way we want them to. Here we go. Over the last 4 or 5 years, this is a problem that a lot of teams around the world, including ourselves, have been thinking about. And the result has been something of a revolution in our ability to model over very large scales anywhere on the planet. Now, as you can imagine, this has required a whole body of research to be done on all of the various aspects of flood modeling. So we have research into terrain data, we have research into how you might estimate what extreme flows look like for any river on the planet. We have research into what these rivers might look like in terms of their geometry, in terms of their size and location. You have to do a huge amount of optimization of the algorithms themselves to make sure that they can run quickly enough and on very large computers to be able to give us the results that we need. And unlike the example model that I showed you on the first slide, which would have been built by hand, which is typical for an engineering model, if you're building models at the continental scale, you can't build everything by hand. There has to be quite a large degree of automation, and that itself has also been subject to a lot of research. Now, if you look at our website, we have a timeline, and on that timeline, you can click and link through to all of the academic research and papers that we published on these different topics. So I'm not going to go through all of them now because it would take far longer than we have. All I am going to do is touch upon one of these aspects. Go back one slide. There we are. Okay. Which is terrain data, because for flood models in the developing world, in Asia, terrain data has generally been the biggest challenge that we face. Now, the best available open source terrain data set for flood modeling is something called SRTM, which stands for the Shuttle Radar Topography Mission. This was a data set collected by the US government using the space shuttle. They attached a radar to it and flew it around and around and around the planet, picking up returns from the radar and using those to estimate the elevation of the Earth's surface. Now, despite it being the best open source data set that we have available, in its raw, unprocessed form, it is unfortunately pretty hopeless for flood modeling. And this is because there are a large number of errors that are associated with this data set. The radar becomes badly scattered when it interacts with vegetation or buildings on the Earth's surface. So that makes forests and cities appear like to be hills. And you can also see, even from this large image here that we have of the Mekong Delta, something very obvious. You can see stripes that are running from east to west across the delta here. And those were caused by the space shuttle itself pitching and rolling. And you can imagine if you simulate water flowing across something like that, you will get some very strange results. Fortunately, because it's an open source data set, because it's been around for a while, there's been a huge amount of research done on it. And okay. And you can see the amount of correction that has been achieved on this data set. We've been a part of that research push, and last year we published, along with some colleagues in Japan, the most recent and most sophisticated reprocessing of SRTM. And this has brought the errors down to a controllable level whereby we can produce sensible flood simulations all over the planet using this data set. Now, there's a point I'd like to make here about resolution. For flood models, resolution is often the first thing that's quoted. This is a 90-meter model or a 30-meter model or a 10-meter model. But actually, you have to be very careful with that metric, because the critical component for a flood model is actually how precise a pixel is. So it's the vertical precision rather than the horizontal precision. I like to make an analogy here to the camera that you might have on your phone relative to a professional camera that a professional photographer may use. Now, cameras on phones these days have got very high megapixel counts. You can have a 10 megapixel camera in your phone. That camera will produce the same number of pixels in an image as a professional camera will produce. But that doesn't mean the two images are actually the same quality. They have the same number of pixels, but every single pixel in the phone camera image won't be as precise as its corresponding pixel in the professional camera's image. And that's very much the same with terrain data. So SRTM is actually available at 30 meters now, but there's not a lot of point in using it at 30 meters because at the individual pixel level, there's simply too much noise. And you have to do a huge amount of smoothing and processing to make it useful. And if you're doing that, there's not actually any point in then running the simulation at that resolution, because all you're doing is giving a false estimate of accuracy, it's false precision. So this data set is available globally at 90 meters, and we believe that's the most suitable resolution to use it at. And it's indicative of the quality of the data and what you can do with it. Now, if we can just control these slides from advancing too far. Okay, so that's one little example, terrain data. And as I said, there's a whole aspect, a whole number of aspects that have been researched and improved. And these are all pulled together into frameworks. And one of the critical things to do is then validate, or attempt to validate at least, the results produced by these frameworks. And that's something that we've done in the US. We've chosen to do it in the US because the US has the largest available catalog of engineering flood models. All of the flood models produced by the US government for the FEMA maps. And we pulled every single one of those together using a fantastic tool produced by Google called Earth Engine. And we checked our map for all of the US at the 100-year return period to the FEMA maps. And we found very good correspondence. We found very high hit rates up in the mid-80s for the continent as a whole. And this gives good confidence that the model is performing as we'd hope, and actually it's approaching the quality of local scale models. And the full details of that validation and study are available at the reference below. And again, that's also linked to from our website, which is www.fathom.global. And I think the important thing to point out here is that everything we're talking about is referenced and is peer reviewed and is available in the academic press. And we've made these papers all open source, so anybody can look at them. And we do that to try and be as transparent as we can about models that we're producing and the quality of those models, because these are relatively new things. They definitely do have areas where they perform well and areas where they do not perform well. And it's really important for end users to understand the strengths and the limitations of these tools, and also to watch as they progress, because actually the applicability of these models is changing all the time. Now, in terms of what's available in the box, as it were, on the Oasis hub. So if you pick up one of our flood model data sets, what you will get is a 90-meter spatial resolution product built on the terrain data that I introduced earlier. It's available for 10 return periods, ranging from the 5-year to the 1,000 years. All return period, all channels, from the very largest rivers like the Mekong all the way down to a catchment size of about 50 square kilometers, so really very small streams, are simulated explicitly with our framework. The model simulates both fluvial, so riverine flooding, and pluvial, so extreme rainfall. And the methodology, as I've said, is open, transparent. You can have a look at absolutely everything that goes into the model and the assumptions that we make and how it's used. And it's been fully peer reviewed. So this is state of the art in terms of where research has got to in this field. So that's a little introduction into the data, and we thought it might be good to just give a few example use cases. So, of course, there's insurance. And, you know, there are the typical things that you can do. So you can help, the data can help for underwriting purposes, or it can help for portfolio management. And because the methodology is consistent across territories, you can get a very comprehensive and consistent view of risk. Now, with this global data, when it comes to underwriting individual assets, you do have to be careful because, as I've said, the data is limited in terms of precision because of the terrain data that we have available to work with, and because of the other information that we have about things like flood defenses. A lot of these are estimates rather than direct observations because comprehensive data sets of things like flood defenses and river structures aren't available across Asia. So we have to estimate where these are and how comprehensive they are. So if you're going to use this sort of data for underwriting, if you don't have anything else available, it's certainly useful, but you want to be careful about using it at an individual location and treating it as an absolute truth. You need to think of it more as a guide, as a decision support tool, because data in Asia isn't yet of the same quality as you might have in the US or the UK, or within Asia, Japan as well has very high quality data available for it. Outside of those areas, you have to be a little bit more careful with how you're using the data. Now, if you move out to portfolio management, it starts to get more easily applicable because the law of large numbers simply means that any errors for individual assets will likely be cancelled out by opposite errors from other assets because we know there isn't any significant bias within the model. And so it's more easily applicable to portfolio management. One of the things that we've been using the data for is disaster response. So we did a lot of work during the hurricane season last year. As you know, there were 3 particularly bad hurricanes. And for example, for Harvey, we produced a whole series of footprints using this data set, driving the model with forecasts from the US weather services, and then updating that with observations to produce event footprints. And that's something that we can do all over the world, and it can be very useful for first responders. It can be very useful for the insurance industry when they're looking to start to set up the claims handling and determine their capital strategies for large events as they're happening. We can use it for large-scale risk analysis. Now, this can be something that's done by governments. So, for example, in the US, trying to fill in the gaps where FEMA coverage doesn't exist. But it can also be extremely useful for large corporates who have assets all over the planet. So you're thinking about things like supply chain risk, you're thinking about asset risk, you're thinking about continuity of service. So we do have blue chip clients who use our global data set to actually look at their operation holistically and look at any risks that they may not have factored into their operational practices. So this can be a very useful application of the data for perhaps for clients and markets that haven't really been using it beforehand. And then international development, we do quite a lot of work with the World Bank, for example, and typically the data is used for these sorts of projects to screen possible sites for infrastructure development, or to look at where populations are growing into risky areas. So we worked in Vietnam and Bangladesh, Belize, Tanzania, Sao Tome for these sorts of projects. And you can use the data not to make engineering decisions. It's not yet of a high enough precision for that, but you can certainly use it to identify where your priority areas are for more detailed local study. So you can identify risk hotspots. And yes, I think that's the last slide that we have at the moment. So I'll probably hand back over to Jim now.
Thank you, Chris. Thank you very much. What I'd like to do now is, before we look at how to get the data, just take a moment to explain what the data is. Chris mentioned that we have two versions. We have two data sets, a standard and extended, and both data sets contain fluvial and pluvial undefended data. And each is a layer. So we have 20, 50 and 100-year return periods in the standard data set. The extended data set has everything that's in the standard data set, but what it also introduces as well is 5, 10, 75, 200, 250, 500 and 1,000-year return periods. Okay, if you mouse over to the oasishub.co/your-city-your-future, don't worry about that, because the whole webinar is being recorded, and we'll send you a link to the recording and also a copy of the slides in PDF format as well, so you'll be able to access directly from the presentation. So the campaign page, as we're calling it, gives you an idea of what regions we'll be providing data for, and then you can choose which city that you're interested in. And if your city isn't listed, there's a link to a form you can fill in and tell us what city you're interested in, and we'll get back to you with the timescale and a price. And then choosing a city gives you a little bit more background to the social and economic challenges it faces, with links off to standard or extended data sets. So if you go into, in this example, an extended data set here, you'll see a little get price button. If you click that, and you'll be taken to a very simple form, which just allows you to provide some information, your contact details, and we'll get back in touch with you very quickly with a link to make payment and a link to download the data as well. So that ends the main part of the webinar. Does anybody have any questions that you'd like to ask us right now? Chris, I have a question for you. How do you start? What's the kind of the most difficult problem to solve when you're creating a flood model for Asia?
Sorry about that. I seem to be muted out, but I think this is working again now. Yes, it is. So when we started to think about this framework, we were sat in a PhD office at Bristol University, and we actually sat down and with a large empty whiteboard and wrote down the 5 key challenges that we thought existed in terms of building a large scale flood model. And the answer to that then is that actually there wasn't any one thing, but there was a whole bunch of absolutely critical problems that had to be solved. And the core ones of these were the terrain data. So how do we get a sort of suitable terrain data set for global application, how do we estimate what an extreme flow in any river around the world looks like? Because for the vast majority of rivers, we don't have direct observations of them. There aren't gauges on most rivers around the world. So you can't measure what the 5-year flood or the 10-year flood or the 100-year flood looks like. So you have to come up with some sort of estimate for what that looks like that is plausible and realistic. And then you have to plug that estimate of flow into a model of a river that you haven't been able to measure directly. So that means that you also have to estimate actually how big that river is. What do the flood defenses look like for that river? And the key thing was linking all of those components together into a consistent framework that meant that ensured that any bias in those estimates, because those estimates are always going to have biases and errors in them, doesn't adversely affect actually the behavior of the model. So it was coming up with a consistent approach that was able to behave sensibly when we only had very poor data available. And that's really the core part of our framework. So yeah, and then once you have that basic framework in place, really it's a question of trying to find any other information that's available to refine the various aspects of that framework for a particular site. And obviously that is very site dependent.
Right. Okay. So plenty to think about then.
Yeah. It's I mean, that's one of the interesting things about this field. Unlike hurricane modeling and earthquake modeling, which has been being undertaken on really very large scales for quite a long time now, since the late 80s, really, with the advent of computer CAT models. Flood at very large scales is a really new thing, just because you have to operate at such fine resolution. If I'm stood where I am now and move 10 meters over to my left, I drop about 3 or 4 meters in elevation. And that means that for a flood event, 10 meters to my left might be 3 meters underwater, whereas where I am standing now is dry. So you simply can't model it at 1 kilometer resolution or 5 kilometer resolution, the sorts of resolutions that early CAT models were running at for hurricanes and for earthquakes. You've got to model at very fine resolution. And that makes it massively challenging in terms of data and computation. And that means it's only something that's really been possible to start doing recently. But because it's a new field, there are lots of different approaches out there. The research is very new, it's constantly developing. So yeah, these models are improving all the time and will continue to do so, which makes it a very interesting field to work in, a very interesting field to follow, but I think quite a challenging field for users to keep on top of actually understanding what they can and can't do with the data. Yeah, it's constantly changing.
Great, thank you. Now we are out of time right now, so just to kind of summarize on things, we are recording the webinar, so we will make the recording available, and we will also make a copy of the slides available as a PDF as well. And if you've got any further questions, if you drop us a note to hello@oasishub.co, we'll get back to you very quickly with an answer. So I'd just like to thank you all. I'd especially like to thank Chris for his time and all the work that he and the guys at Fathom are doing. It's fantastic. And if, like I say, any questions, hello@oasishub.co. And thank you for your time today, and enjoy the rest of your day. And we look forward to seeing you on another webinar soon. Thanks, take care, and bye for now.